Hello, and welcome to this ABB Enterprise Software presentation, Balancing Act, Leveraging New Data in the Velocity Suite. This presentation will last 1 hour, and telephones will be muted for the duration. If you have questions, please submit them through the chat or the Q&A window in your WebEx screen. Now I give you today's speaker, Kevin Arnold, Content Manager, Velocity Suite Power.
Excellent. Thank you very much, Dana. Hello, good morning, good afternoon to everybody, and thank you for joining us for this Energy Market Intelligence webcast. We're going to be talking about some new data that's available in the Velocity Suite and how you can utilize it in your day-to-day work. Here's a disclaimer from ABB saying that they're not responsible for anything that's out of whack in this presentation and that you can't redistribute it. As Dana mentioned, my name is Kevin Arnold. I am the Content Manager for the EV Power module inside of the Velocity Suite. I've been working in this industry for about 7-8 years now, and I can say that this is some of the most exciting data that I've ever been a part of. So I'm really glad that you guys could be here to share in this new data with me. Here's a brief agenda of what we're going to be going over today. Basically, what is the EIA 930, who's reporting it, what's being reported, what the schedule looks like, where can you find it in the Velocity Suite, and then we'll get into some of the tools. How can you use it? Load shapes, duration curves, time series, visualization, capacity factors and load ratios, calculating reserve margins, and then I have two pretty quick sample analyses that I put together there at the end. As always with these Velocity Suite webcasts, all of the charts and the graphs that you're going to be seeing were created inside the Velocity Suite. So if you have any questions or would like to have a little bit of training in regards to what's being presented to you today, feel free to reach out to our support line or to me directly. Thank you. All right, so let's start talking about what is the EIA 930. So the EIA 930 is a new federal survey of electric operating system data. It was basically a part of the Federal Energy Administration Act, if that's interesting to anybody at all besides me. But basically what it is 5 schedules of new timely data that's going to give us new look into granularity and transparency into the U.S. energy markets like we've never seen before. What you're seeing right now is pretty much a default data poll for the Tennessee Valley Authority looking at their demand. Notice the dates. This is hourly data that's coming through. This is very timely. Demand is one of the biggest schedules of the survey. It's certainly something that we haven't had for a lot of regions in the United States before. Another part of the EIA 930 is hourly load forecast. So this is going to be posted once per day. And what we can do when we have that is, look at the actual load and the load forecast side by side. Makes for some pretty cool visualizations, and you could do some pretty cool in-depth analysis of it too. What you're seeing here is a 2-day look at Southern Company's actual load versus their load forecast. And things like this are extremely easy to put together with the user-friendly data sets that we have in place, and I'll kind of get into that a little bit more lately. The third schedule that's a part of the EIA 930 is hourly generation. Again, this is something that we haven't had for a lot of the regions in the United States, so it's pretty exciting. This is posted once per day. What you're seeing here is monthly average generation for Pacific Core West, one of those regions that was typically not giving us hourly generation. So it's pretty exciting for us to have this, and we can look at it side by side with our average loads. A little bit later, I'll get into some of the things that having our generation and load side by side can, enable us to do with analysis. The fourth schedule that's part of the EIA 930 is interchange in between balancing authority areas themselves. So what you're seeing here is the interchange on 2 different transmission paths, CPLE to Duke, which is Progress Energy East into Duke Energy Carolinas, and the inverse of that, which is Duke Energy into Progress Energy East. All interconnections that are inside the United States are going to, they're going to exist twice. There should be a mirror image of every transmission path that is being reported to the EIA on this. In the top there, I put a little bit of a visualization of what this actual path is. You can see it's in, North Carolina, and basically you're seeing hourly flows of energy along that path, either going from Progress Energy into Duke or the opposite way, going from Duke into Progress Energy. The fifth and final schedule for the EIA 930 is the net interchange for all balancing authority areas. What this is basically the summation of all of the interchange points for any given balancing authority area. So here's a week-long look at the major balancing authorities in Florida and how they change. Positive value in this case is going to be an import. Negative value is going to be an export. So, you can just take a look at it and see, it looks like Seminole Electric Co-op is doing quite a bit of exporting of energy. Florida Power and Light and Progress Energy Florida, on the other hand, are doing a lot of importing. Kind of a cool one to look at there is JEA, and it looks like, about 3/4 of the way through the week, they were exporting energy, something happened, and they started importing energy. You could use this as a starting point to start to figure out where to look next for your analysis. So let's talk about a little bit about why this is significant. Why is the EIA 930 such a game changer for the United States energy markets and transparency into them? Well, before we had data similar to this available for sections of the United States, mainly if a part of the United States existed inside of an ISO, we were going to be able to get data for their hourly demand. We were going to be able to get demand forecasts, and we were going to be able to get hourly generation for some of them, but not all of them. Also, select balancing authority areas were making this data available, but we have a lot of white space, as you can see on this map of the United States, as far as where we were able to get this data from. Well, now our coverage looks more like this, where every balancing area, every balancing authority in the United States is being required to report on the EIA 930. Now, the EIA says that we're going to have 66 balancing authority areas that are going to be reporting real-time data. What we've been able to observe in our data collection process is that we have 56 that are reporting in real time right now. For those of you that don't know what a balancing authority is, basically it's a region that's responsible for the resource planning and maintaining the balance between the load, the interchange, and the generation for the area that falls within their footprint. So there was data that existed before that had the interchange, that had the hourly demand, and had the demand forecast, things like that. It was called the FERC 714. They still publish the FERC 714, but the big issue with the FERC 714 is that it's an annual file. It comes out once a year, and it's at quite a significant lag, right? It's about a 5 or 6 month lag as far as the reporting goes. This here is basically my representation of, I was comparing the reported EIA 930 values from 2015 to the monthly peaks that reported on the FERC 714. And at least for Duke Energy Carolina, you can see that they're reporting very good data. This is almost spot on, and this is aggregating our hourly data to a monthly level and still finding that it matches up pretty well. Now, I'm not going to point fingers or anything like that, but I can say that not all balancing authorities match up quite this well to the 714 data, but for the most part, what we're seeing is pretty accurate and pretty clean data coming through right off the automated systems from the balancing authorities. Here's a recap of the reporting schedule for the 930. So every hour, they're posting demand for the previous hour. So that's coming through every hour. We're scraping it all the time. Every morning before 7 a.m. Eastern Time, they're posting a set of data which includes the demand forecast for the current day, the hourly demand, net generation, and total interchange for the previous day, and then they're also posting the net interchange for each transmission path on a 2-day lag. Now, the EIA came out and said that they were going to be basically grabbing this information and making it available right from the automated systems of the balancing authority areas themselves. They would do this in order to basically lessen the burden on the reporting entities that are going to be required to report all of this data. We do see a couple of issues with that, which I'll get into in just a little bit. As far as where to find this in the Velocity suite, there's 4 data sets that it's going to exist in: demand by balancing authority area hourly, historical demand forecast by balancing authority hourly, hourly regional generation by fuel type, and transmission paths hourly flows. I would highly recommend that you use the sort and search functionality in the intelligent query tool if you're trying to find this data. If you search for EIA 930, you will find all 4 of these data sets, and they're fairly user-friendly and easy to navigate. And of course, if you ever have issues, don't hesitate to call our customer support, and we have a dedicated staff of analysts who are always willing to help out. So back to the issue of giving us as-is data. This is data that came in right from the EIA 930. Before any type of modeling, this is what it would look like in the Velocity suite if we allowed this to go into our product. You can see that this appears to be a bogus outlier. The demand is completely out of range, and it throws off the scale for this entire chart. Additionally, if you were going to do any type of aggregation on this, if you're going to roll it up to a daily or a monthly level, it would skew your results, and it would impact any type of model that you were doing or any type of analysis that you were trying to run. So a big value add of the Velocity suite is we are taking this data and we're cleaning it up. We're putting it through some of our own modeling processes in order to make it usable. You can see that after you remove that outlier and replace it with an acceptable value, what you have is a nice clean series of daily load shapes over a week. You can even identify a pattern of increasing load as the week goes on, and it makes this data usable, for your analysis. It makes it visually appeasing. It's much cleaner once it's gone through the Velocity suite's modeling processes. All right, so now that we've been through basically what the EIA 930 data is, what it entails, who's reporting it, and where to find it, let's talk a little bit about how you can use it, right? So the first thing I'd like to talk about is load shapes. Load shapes are a pretty basic idea that when you're talking about, hourly demand data at a granular level like this, load shapes are going to be very important. So basically, it's just a curve that represents load or demand as a function of time. That's what your load shape is. So this is a 1 day's worth of load on Florida Power and Light on the 28th of July. You can see that I've just got them ordered hours 1 to 24. All load shapes are going to have really the same basic characteristics. You'll almost always be able to identify a base load. You'll almost always be able to identify a peak load. Along with that, there are a couple of time things that you should take into place. One is the rise time. What is the amount of time that it takes to get from that base up to the peak? And the other way around, what's the fall time? What does it take to get from the peak down to that base demand? Another thing that oftentimes can change is the high load duration. Is there a sustained period of time where you have high load, or is it really a short period of high load duration where you're hitting your peak, but you're only hitting your peak in 1 hour, and it's not really an extended period of time? The Velocity suite allows you to easily pivot, unpivot, aggregate data. This large amounts of real-time data can often be difficult to work with, but because of the way that our intelligent chart tool and our intelligent query tool are set up, it makes it very, very user-friendly in order to grab data like this, make it visually appeasing, like I mentioned earlier, and make it fun for analysis. This is one that I like to do for a lot of the different regions. So this is the average June load shape series by day of week for Florida Power and Light. So every different colored line that is appearing here on this load shape is going to represent a different day of the week. You can see Saturday and Sunday, it's a little bit different. Their peak load is occurring a little bit earlier in the day, and it looks like their base load is also occurring a little bit later in the day. So, these are just kind of different ways that you can think about these load shapes in order to, figure out whatever type of analysis you may be doing. So load shapes also have another distinct characteristic, which is that they're very unique regionally. They're going to vary a lot from place to place. So looking at the different regions and looking at all these different load shapes will help us to identify different patterns that we can use in our generation resource adequacy for our supply and demand planning. So what you're seeing here, these are 4 annual average load shapes from all over the United States. In the top left, we have ISO New England. Top right, we have Florida Power and Light. Bottom left, we have WAPA Desert Southwest region. And the bottom right, we have Public Service Company of Colorado. Now, you can see that all of these shapes are very different. You can see that the peak load is going to occur in a different hour for almost all of these, and that the scale of that y-axis is greatly different based on, the size of the BA, which is not necessarily surprising. It's something that you would expect. Let's see. Along with the regionality aspect of these load shapes is the seasonality. So look at Florida Power and Light, for example. Notice the differences that are caused by, just the difference in the seasons. You're seeing peak load occur at a different hour. You're seeing a steeper rise time, but you're also seeing a shorter peak load duration during the winter, and just a little bit of a different shape in general. You see a similar change in New England. You have a much shorter high load duration again, and kind of a funky little shape there when you compare summer and winter. Public Service Company of Colorado, again, you have an altered shape when you compare the average summer and the average winter load shapes. Look at the time of day that the peak load is occurring. In Public Service Company of Colorado, it looks like it's occurring, a couple hours later in the day in the winter. So when you're doing your generation planning as a balancing authority or as a, resource adequacy planner, these are things that you would want to take into account. And then there's WAPA Desert Southwest, and I was pretty blown away by this load shape actually when I ran the averages for their winter load. What I actually see is that their peak load is occurring in the morning. It's not something that I had seen before, so I thought I'd throw it in there as just kind of a note on how they can change region to region and especially seasonality in there. So besides load shapes, another way to visualize load is what's called a load duration curve. So this is something that's possible to do inside the Velocity Suite intelligent charting tool, specifically using that hourly demand by balancing authority area data set. You can easily make a graphic that looks just like this. Everything that's on the underside of this curve is going to represent consumed energy. A slice and its height is going to represent an increment of load, and the width of that slice is going to represent the duration or the amount of time that it took place. So this is a duration curve that I put together based on hourly data from Q2 of 2016 for the Ohio Valley Electric Co-op. So pretty interesting. It's just another way that you can visualize load. A lot of people are preferring to use these sometimes in their analyses, so it is something that is made available in the Velocity Suite. Another thing that I like to do is look at error, right? When we're talking about forecasting versus actual load, how good are we about forecasting our load? How efficient are we? So it makes it, the data that's available in the historical demand by balancing authority area data set makes it very easy to view load and load forecasts side by side. And if you have them side by side, it's incredibly easy to calculate the percentage of error. What I've got here is averages for Tennessee Valley Authority for a one-year period, and you can see that for any given month, their average percent error is anywhere from 3.5% to 5%, which is pretty good. That means that most of the time they're getting pretty close to being able to determine what their actual load is going to be at any given hour, which will make it easier to identify their peak load, base load hours, and really help with all of that generation planning. Like I mentioned, this data is hourly, so if you want to calculate this for every hour of the day, you absolutely can. Here's just a zoomed-in look, really, of that TVA data with the percent error calculated in there. You can see that, at any given hour, they're pretty good about forecasting what it's going to be. It's important to note that when we have access to this type of data where it's very transparent and very granular, it ought to help us decrease the amount of errors that we see, improve our forecasts, and thus improve our efficiency and our ability to successfully plan for the future when it comes to generation. So this is kind of one that I put together just for fun. I was just kind of goofing around, and I wanted to see how good the United States was at a national level as far as forecasting the demand that was coming through. So you can see at a national level, we're quite a bit higher than Tennessee Valley Authority was, ranging anywhere from about 7.5% to 15%, but for the most part, not a ton of errors that are coming through on this. So let's talk a little bit about visualization. Another piece that came into the Velocity Suite via this EIA 930 data is two new map layers that were added to one of the most powerful tools in the Velocity Suite, which is the EV Energy Map. We have two new layers. One of them is called BA Interchange Points. The other is called BA Interchange Paths. The points in this case are represented by the blue dots. The paths are represented by the lines. If you look at these zoomed-in regions of the Pacific Northwest and of Florida on this chart, you can see that there is quite a bit of complexity, and there's a lot of interconnections that are involved in these areas where there's a lot of adjacent balancing authority areas. So, that data goes hand in hand with the interchange data that's being reported in part of the transmission paths hourly flows, and of course it's all data mineable to and from the intelligent query into the map. So, all right. This is just an example of how the Velocity Suite can help you visualize the data. What this is here is exports of electricity in Florida over a one-day period. I think July 25th is the day that we picked. But this is exports in all of the different BAs that are existing there in FRCC. You can flip it around, show all of the imports. This is something that can be done pretty easily with the powerful tool that is the EV Energy Map. Notice kind of one odd point here is that you do not see a line connecting the new Smyrna Beach Balancing Authority area to the others because we have not had a transmission path for them reported yet. But we expect to see all of the balancing authority areas that we're supposed to report according to the EIA start to come on pretty soon. So, the primary responsibility of a balancing authority is going to be to balance the system, right? So at any given moment, your load should be equal to the sum of your generation and your interchange. Because of the nature of electricity, the energy that is produced must be consumed and used at the same moment that it's being produced. That makes balancing very difficult. So here's a look at Mid-Continent ISO, MISO's generation, interchange, and load, all in one series in one chart. Like I said, the Velocity Suite makes these very, very easy to put together. This is exactly what you would expect it to look like. As the generation starts to get closer and closer to fulfilling the load, the amount of energy that's being imported is going down. Here's a look at Pacific Core West, just a little bit longer of a series, and you can actually see a couple of times where they had to switch over from importing data or importing energy to exporting energy. So I find this to be very helpful, and these are all default items for the hourly regional generation by fuel type data set, which I mentioned earlier. All right. So another useful tool, something that a lot of people are doing with this data when they're looking at it, is looking at the capacity factor. What is the capacity factor? Well, the capacity factor is basically just your amount of actual generation as a ratio to what your potential output could have been as a percentage. So what is your maximum possible generation for any given time period? What was your actual generation for that time period? This is an example where I was calculating the capacity factor for Louisville Gas and Electric on an hourly basis. I know that when people are looking at these capacity factors, they're oftentimes aggregating them to monthly or annual, quarterly levels, things like that. This is possible, but it's also possible, because we have the hourly data, to go ahead and do it here, at an hourly level. So it really adds to the ways that you can look at this. Now, one thing to keep in mind when you're looking at these capacity factors, these are going to vary drastically based on the fuel mix of the region. If you have a region that has a high amount of wind, solar, renewable energy, you would expect to see a lower capacity factor, because these resources are not going to be able to generate all the time. So they are going to change your capacity factors. Let's see. Here's a look that I got some of this data from the FERC 714, and that's what I'm using here for the available capacity numbers. What I really want to highlight here is that the available capacity is going to change from month to month, right? There are many different things that can cause this. Most notably are going to be the weather when it comes to wind and solar and even hydro. The other is outages, right? We'll get into an example of an outage a little bit later. We start talking about Palo Verde, but outages and the availability of capacity can have a large impact on what your available capacity for a region is, and as a result, what your capacity factor is going to be when you calculate it out. Another important analysis tool that is enabled via the FERC 714, the EIA 930 data is the reserve margin. Your reserve margin is a measure of excess capacity. It's often measured as a percentage, and this is something that you will see quite often if you are reading about supply and demand, especially when you're looking at these balancing authority areas. So the way you calculate a reserve margin is basically it's your capacity for any given time, your available capacity, minus your demand, demand being your peak demand for that time period, and then that total divided by your peak demand again. It'll give you basically your excess capacity as a percentage. Typical reserve margins in the United States are going to range anywhere from 6% to 40%. It's also going to depend on how you're going to aggregate this data. You can see in this example that I have here of South Carolina Electric and Gas Company, the reserve margin gets as high as 70%. Well, a big part of that is because I'm calculating these on a weekly basis. That's not typically the norm. If you were going to average this out, it would probably be inside of that range that I just mentioned. NERC right now has targets that it's set in place for all of the different areas, all the different NERC regions. And they're going to vary anywhere from 15% to 30%. Most of their regions are currently falling inside of those reserve margin goals that were set forth. So now let's take a look at CAISO. CAISO is a pretty interesting one when we talk about the reserve margin because they have such a high amount of load. They have so much demand on that system at any given time. It makes calculating their reserve margin pretty interesting. So, like I said before, well, I guess let's start. In order to do this, I put in a couple of capacity modifiers in order to figure out what the actual peak capacity for CAISO is going to be. So I'm assuming 20% operation from wind, 30% operations from hydro, and 50% operations from solar. Figuring out your reserve margins is quite a bit of science, quite a bit of math, and a little bit of art as far as what I've been able to determine so far. So, you know, there's so many different ways that you could do it, and you'll come up with different numbers, you know, based on how you put out that capability. So what I use is the available capacity for CAISO here was about 49,000 megawatts. The peak demand for the month of July during that time was 46,000 megawatts. We calculated out, and what we see is that CAISO has a pretty low reserve margin, 6.4%. Means that they've only got, you know, 6% of excess capacity on their system when they're at that peak load. They're getting to that point where it could be critical. It could have some issues associated with it. Luckily for CAISO, they have a lot of coordination and cooperation with their adjacent balancing authority areas, and what they're able to do is supplement their excess load by importing data from some of the other regions. The CAISO EIM, or Energy Imbalance Market, played a big role in helping to stabilize some of the interchange that's going on there in CAISO. So the last real tool that I'll talk about before I get into some quick sample analysis is what's known as a load ratio. Like I said, it's another useful measurement. So what the load ratio is for any given time period, what is your load divided by your maximum possible load. So if you were going to be operating at your peak load for a given time, that's going to be your denominator right there, and you're going to just divide your load by whatever that maximum peak load would be. So basically, it's going to be a measure of variance and volatility in between these different load shapes that we see. This is an example where I've got Nevada Power Company and WAPA Rocky Mountain put on the same series here. This is a nice looking cowboy hat. You can see that the result is that you get a lower load ratio for Nevada Power Company because there's that bigger gap in between their base load and their peak load. For WAPA Rocky Mountain, there's not as big of a gap in between that base and that peak, so they're going to have a higher load ratio. What does that mean? That's, you know, nice to have those numbers next to them, but what does it mean in real life? Well, in real life, it means that in Nevada, they have to have a different type of generating fuel mix available at any given time. WAPA would be able to satisfy most of their load if they're just running base units with a couple of peakers here and there, maybe some wind, and they'll be fine. In Nevada, that's not going to be the case. In order to ramp up or ramp down quickly to meet that potential peak demand, they're going to have you know, gas-fired units that they can turn on at the flip of a switch if necessary. They're going to have to do a lot of planning as far as their resources and what their generating fuel mix goes in order to be able to meet that peak demand, I guess, more swiftly than WAPA would need to do. So those are basically the tools that I've kind of outlined as far as, you know, what people are using from day to day when they're looking at this information. I think that there are definitely quite a few more that I was not able to cover here, but you know, we're always looking for new suggestions from our clients as far as what they would like to see and value adds that they would like to get out of this new data that's being made available to them. So now what I'm going to do is I'm going to talk a little bit about some cross-product stuff and talk a little bit about natural gas and how you can use some of the data that's already available in the Velocity Suite side by side with this new data to, you know, come up with some patterns, come up with some ideas for analysis. So I'm going to pick a region. I'm going to pick New England ISO. The reason that I'm going to do that is because I know that New England has quite a bit of reliance on natural gas when it comes to their generation of electricity. All right. So here's a look at the day-ahead ICE gas price for the Algonquin City Gates, which is right outside of Boston, versus the max temperature in degrees Fahrenheit. You can see that the weighted average index, the price of natural gas, is incredibly responsive to the temperature in Fahrenheit. That's kind of as you would expect. You know, as weather changes, you're going to have a different demand for natural gas, and the price is going to fluctuate. So here's a chart that I put together using a data set that's derived from our operationally available capacity data. This is the daily natural gas demand by customer type data. So for the New England states that are a part of the New England ISO, this is what their deliveries to customers, to end users, look like on any given day. You can see that the biggest recipient of natural gas in New England by far is going to be the electric power plants, hence why their generation is so reliant on natural gas. Now, when you put this into a series with that EIA 930 data, you can see that it's almost instantaneous. When the gas is delivered, your load and your max load are going to increase right there with it. And so what do we see? Well, now let's look at the load with the weighted average index price. So along with what we saw earlier as far as the responsiveness to the weighted average index price to changes in the weather, we also see that the average load is extremely responsive to changes in the weather, particularly here in New England. This is a really good example of it. It's very easy to visualize this, but it just kind of goes to show that changes in the weather, particularly in a region that is as responsive to prices as New England, you're going to be able to visualize that using a combination of data that's already available in the Velocity Suite with data that's available via this new EIA 930 survey. So for my final kind of sample analyses here, I want to talk a little bit about what happens when one of the largest units in the United States goes down, right? So back in April, Palo Verde Unit 1 at the Palo Verde Nuclear Station in Arizona was powered down. It was 100% shut off, Unit 1 was, for about a 5-week period. This was not unplanned. This was scheduled maintenance and refueling. It happens quite often. You can look at the NRC reactor status data set in the power product if you'd like to. But how does this affect the generation, the interchange, and the balance for these areas? So this data from the 930 gives us the ability to take a little bit closer look at this, and it gives us the ability to do that in real time. So as you can expect, obviously, the generation for the Arizona Public Service Company dropped significantly. Arizona Public Service Company is the majority owner here of the Palo Verde Nuclear Station. They are not the sole owner, but they do own the majority of the capacity of the plant. Now, I started digging into previous 714 reports and tried to figure out who all owns a part of Palo Verde, and I got to tell you, it's pretty unbelievable. There's like 15 or 20 different owners that exist or that are reporting at least some amount of generation from Palo Verde directly on their FERC 714. But the ones that I was really able to identify patterns with, it was really Arizona Public Service that was impacted the most. So what happens when the generation from Arizona Public Service goes down? Well, they are typically a huge exporter of electricity. They're, exporting all the time in 60,000 megawatts, no sweat. Well, when that drop happens, it looks like, something has to change in order for that to be adjusted for on the electric system. I brought in the Salt River project here. This is an interesting one because Salt River is actually a partial owner of the Palo Verde nuclear station. But when I brought up the series of the hourly generation for Salt River, you couldn't see any drop in the generation at the Salt River project. That leads me to a couple of things. I think that one is that either their ownership is so insignificant that it's being overshadowed by other assets that they own, or their ownership at the Palo Verde nuclear power plant is in units 2 and 3 and was not affected by the shutdown of unit 1. So as you can see here, as you have a sustained amount of time where Arizona Public Service Company is not able to export, they've got to start importing, or somebody else has to try to make up that export, and it looks like, at least to some extent, Salt River Project was one of the areas that was doing that. Now, if you look at the net interchange for both Arizona Public Service Company and Salt River Project, you can see it pretty easily, right? The orange line, and it's moving in towards the middle there. That's that drop in generation, really. And the green line, Salt River Project, kind of slowly moving down towards the middle. They're going from being a net importer even to having to export. And then the blue line there represents the actual interchange path that exists there in between Arizona Public Service Company and Salt River Project. So by, I guess, digging down, you can really see that, one of these, the interchange for one area changed. They weren't able to export as much as they normally had in the past. How was it affected as far as all of the balancing authority areas in the region go? That's going to be much more difficult to discern. More than likely, what happens here in terms of the actual outcome of the Palo Verde nuclear outage is that we see many small adjustments made by all of the adjacent balancing authority areas. It basically lends itself to, this is an extremely complex system that we have in place. But this new data from the EIA 930 gives you the tools to figure out what to analyze, where to start, and will give you the granularity and the transparency into the market that you need in order to start your analysis and help to improve the efficiency of our system through accurate planning, resource adequacy, and basically sustained generation. So I guess that's pretty much everything that I have for you guys as far as I put together. I know that I've thrown a lot of charts at you in the last 35, 40 minutes or so. Like I mentioned, all of those are available via the Velocity Suite. If you have questions about how to recreate those, just let us know. We're always looking to improve our data, so if you have suggestions for additional items that you'd like to see or ideas about how we could be modeling this data, absolutely. Feel free to reach out to customer support. Feel free to reach out to me, and we will address them as soon as possible. So now at this point, looks like we've had some questions come through here on the chat line, so I'm going to go through and see what I can answer. Let's see, first question, how can we break up the larger balancing authority areas like MISO? I understand that. So, yeah, when you look at the load or the generation from an area like MISO, it could be very, very daunting because it is such a large region. There's so many customers that are going to be encompassed in there. Right now, unfortunately, the granularity is at the balancing authority area level. However, the EIA, once every 2 years or whenever they feel like it, puts out proposed survey changes. They had 2 proposed survey changes for the EIA 930 as a part of their last round. One of those is to have this data start to be reported at the sub-BA, the local BA or LBA level. The other proposed change was for the generation, the hourly generation that's being reported, to be reported at a fuel type, generation by fuel type level, which would be very cool to see. Let's see. I've got another one here. Is there going to be a way to tell which records have been modeled? Yes, there is. We can put a flag in place in the product that'll basically show you which records have been adjusted by us, which records came straight as raw data from the EIA. We have that in place in our table structure and would not be difficult to implement if it's not already. I think it might even be an available item already. Are the error calculations made available as items in the data set, or were there manual calculations involved? That's a great question. The error calculations are not involved. They are not an item that's available in the data set, although it would not take much for us to create them as one. What I did in order to do that was I created a custom item inside the intelligent query tool. So I didn't have to do, I didn't have to bring it out into an Excel spreadsheet and calculate a column and then bring it back in or anything like that. I was able to do it all inside the Velocity suite, but it was a custom item that was taking a % of the difference from the forecast and the average. Let's see, can the capacity and reserve margin be done for future forecasts or only historical data? That's a good question. So, yes, you could do a capacity or a reserve margin for a future forecast. What you would have to take into account there is probably the most difficult part about that is going to be determining what is your available capacity in the future. Luckily for you, the Velocity suite has some pretty good data as far as what's planning or being planned to come online for a lot of these regions. So you can use our generating unit capacity or our new entrance data set in order to determine what the planned future capacity for any given region is going to be, and use that in order to create those forecasts. I hope I'm understanding that correctly, but yes, you should be able to calculate your capacity and reserve margins for forecasted data as well. When was this data first collected and reported under 930? Good question. So the first data that we have available in product is March of 2015 and forward. It was first reported, I think, in May of 2015, and they were, just came out with a couple of months at the same time. But it was very much preliminary data at that time. Right now, we're seeing a little bit of the inconsistencies that were first, happening with the EIA's reporting start to go away, and we've been able to refine our data collection and data modeling in order to try to clean up the data a little bit. So I think that we should be good. Are we going to post the presentation? Yes, anybody that signed on is going to get a copy of the slide deck. You'll also get a copy of my presentation. And I'm pretty sure that ABB has been posting all of our webcasts on YouTube. So if you want to search on YouTube, you should be able to find it. Dana will let you guys know via email, I'm pretty sure, after the webcast is complete. Let's see, I've got another one. Is there any plan to make the 930 data available intraday within the next 2 to 3 weeks? As far as within the next 2 to 3 weeks goes, that might be a little bit difficult for us because of our release schedule. I think that we could do it. The Velocity Suite's going through a major migration right now where we're moving to a cloud-based platform. I'm sure that for you users out there, you've probably gotten more and more used to using VSO. You see that some of our data is already being updated intraday, and I think that with the amount of interest and questions that we've had about the 930 data, I think that it'll be made a priority going forward. So I could see that happening, but I can't make any promises as to whether or not it's going to happen right now. I got another one. How is the data you used for average hourly generation by BAA reported, or Is that how it is reported? Oh, okay. So I think I understand what you're saying there. I was aggregating the data and I was averaging it myself. So they're giving us one generation number per hour. I was in several of my charts aggregating it to a weekly, monthly, daily level, and then taking either the average generation or the max generation or the sum generation. These are all items that are available inside the intelligent chart query, well labeled so that they're easy to use. Let's see, I think that was most of the questions. Is it all one big number for MISO and PJM, or do they break them down? Yeah, so they are giving us one big number for MISO and PJM, unfortunately, like I mentioned, but it does look like there are plans for the EIA, as long as they don't get too much blowback from the reporting entities right now. It does look like they're going to plan on breaking that down into a smaller regional level. I do not think we have any more questions. If you guys have anything, submit them. If not, anything that you guys have that comes to mind, in the coming days when you're dreaming about 930 data, feel free to send me an email. Like I said, reach out to the customer support line. Let us know. We want feedback on how we can make this data as useful to you guys as possible. So anything you say, let me know. See, I got another question in just right now. How far back does historic data go? Like I said, it goes back to March of 2015. Yeah, right on. Well, thank you guys for joining today. I had a really good time letting you know how excited I am about the EIA 930. I hope that you guys are all in the same boat, and hopefully we'll get some good questions, suggestions from you guys over the coming days about how we can improve this data and how you guys are using it. Thank you very much.